What if an interstellar object travelling faster than any spacecraft ever built were on a collision course with the Sun? Not just another comet, not a stray asteroid from our neighbourhood, but a true outsider born in the cold shadows of another star system. This is the scenario we're going to explore the idea that 3I Atlas, a mysterious wanderer from deep space, might one day plunge into the very heart of our solar system. At first, the idea sounds harmless. The Sun is a giant. It devours small comets and chunks of rock all the time, barely noticing. But 3 Atlas is different. It doesn't belong here. It moves at extraordinary speed, carries unknown material, and cuts across our solar system without the familiar, predictable orbit of homegrown objects. When something like this heads toward the Sun, it raises questions far beyond the ordinary. So what happens if this collision were real? Could the Sun, a star that has burned steadily for billions of years, be shaken by the impact of a visitor from another world? Would it trigger violent eruptions on its surface storms that lash out across space? Could a flare of energy strike Earth, disrupting satellites, shutting down power grids and plunging cities into darkness? The Sun itself would remain, but our fragile civilization could be caught in the blast wave. That's the unsettling part. A collision with the Sun might sound like the safest outcome, better than hitting Earth or Mars, but in reality it could unleash consequences that reach every corner of the solar system. It's not about destroying the star, it's about how the shock of that impact could ripple outward, disturbing planets, moons, and even us. In this video we'll unravel the story of 3I Atlas. We'll look at where it came from, what scientists know about it, and why experts at NASA and other observatories cannot fully rule out extreme scenarios. We'll examine what might happen if such a collision occurred, and how the chain reactions could reshape the solar system. We'll imagine what it would mean for Mars, for Earth, and for the future of humanity. And we'll explore the unsettling possibility that destruction itself might carry the seeds of new beginnings. This is not science fiction. It is a thought experiment grounded in real science, in the mysteries of interstellar objects and the unpredictable nature of gravity. The goal is not to frighten, but to explore. Because when we ask questions like these, we discover how little we truly control in a universe that is vast, ancient, and endlessly surprising. So let's begin with the object itself. What exactly is 3I Atlas, and why did its brief visit spark so much debate among scientists and dreamers alike? In the spring of 2019, astronomers working with the Atlas survey system in Hawaii noticed something unusual. ATLAS, short for Asteroid Terrestrial Impact Last Alert System, is designed to scan the skies every night, searching for objects that might pose a danger to Earth. But this time it picked up something far more intriguing than a local asteroid. It was an object on a path unlike anything in our solar system. This visitor was quickly named 3I Atlas. The 3I stands for Third Interstellar, meaning it was only the third object ever confirmed to come from outside our solar system. The first was Oumuamua in 2017, a long cigar-shaped body that baffled scientists with its unusual acceleration. The second was Borisov in 2018, a comet-like traveller with a glowing tail. And now 3I Atlas joined the list, proving once again that our solar system is not isolated. What made it interstellar its orbit. Normal comets and asteroids follow closed loops around the Sun, pulled back again and again by gravity. But 3I Atlas was different. Its orbit was hyperbolic, open, not closed. In simple terms, it wasn't bound to the Sun at all. It entered our system on one side, swept around in a curve, and then continued back into the depths of space, never to return. That is the unmistakable signature of an object from beyond. Another clue was its speed. Most asteroids in our solar system drift at speeds of tens of kilometers per second relative to Earth. 3I Atlas moved much faster than any typical object born near the Sun. That extra velocity suggested it had been travelling between the stars for millions, maybe billions of years before its chance encounter with us. But while its speed and orbit gave away its interstellar identity, they also made it very hard to study. It raced through the inner solar system in just a matter of months. By the time telescopes around the world were focused on it, it was already fading. In astronomy, observation is everything, and here scientists had only a short window before the object disappeared into the dark. NASA and ESA confirm the difficulty. Unlike planets or asteroids that we can track for years or decades, 3I Atlas was a brief spark. We only had a handful of weeks to measure its brightness, its tail and its trajectory before it slipped away. And that short record leaves a lot of uncertainty. With such limited data, researchers could not be sure of its exact size shape, or even its true composition. Still, some comparisons can be made. Oumuamua, the first interstellar object, was small, only a few hundred meters long, maybe the size of a football field. Borisov was larger, and more clearly a comet with a visible tail of gas and dust. 3I Atlas, based on its brightness, appeared to be bigger than Oumuamua. Some estimates suggested it could be several kilometers across, closer in size to a major asteroid. That made it particularly interesting because an interstellar object of that scale carries far more energy. Its discovery also had another implication. For decades, scientists suspected that countless objects wander, the galaxy ejected from young star systems during their chaotic early years. But until Oumuamua, we had no proof. The arrival of a second and then a third confirmed the theory the galaxy is full of these nomads. The solar system is not a quiet, sealed-off bubble. It is constantly being crossed by fragments of distant worlds, and that raises the real question: what do these visitors mean for us? Oumuamua behaved strangely accelerating in a way that some could not fully explain. Borisov reminded us of the familiar comet that looked much like homegrown comets. 3I Atlas, with its brief blurry record, sits somewhere in between. Its speed size and mysterious origin leave room for debate. Is it a simple lump of rock and ice, a fragment of a shattered planet, or something we have yet to imagine? That uncertainty is exactly why 3I Atlas became the subject of speculation. When an object from another star system suddenly appears, races through our cosmic neighborhood, and then vanishes before we can study it properly, it leaves us with questions. Questions big enough to inspire bold, sometimes alarming scenarios. And that brings us to the central theme of this video. What if such an object, instead of simply passing by, were drawn into a direct collision with the Sun? When astronomers first spotted 3I Atlas, the immediate question was simple. What is it made of? Every object carries a story in its composition. A rock tells of violent impacts. Ice speaks of cold births in distant regions. And a mixture of both suggests a long journey through cosmic extremes. For 3I Atlas, the truth is still hidden. What little we saw left more questions than answers, and out of that uncertainty, several competing theories have emerged. The first and most natural explanation is that 3I Atlas is an ancient comet, a frozen relic from the edge of some other star system. The faint glow observed around it suggested a thin tail, the kind produced when ice meets sunlight. As frozen gases warm up, they escape into space, forming a shroud of vapor and dust. That glow, though faint, hinted that 3I Atlas was not just rock, but at least partly ice. If that is true, then 3I Atlas may have been wandering for millions of years, holding within it pristine material from its birthplace. A comet like that colliding with the Sun would not last long. It would vaporize almost instantly, but not before releasing a vast cloud of gas into the solar atmosphere. Another possibility is that it was not a comet at all, but a rocky asteroid. Unlike comets, asteroids are made mostly of dense minerals and metals. They are tougher, more resistant to heat, and capable of delivering far more energy on impact. If 3I Atlas was primarily rock, then its collision with the Sun would be far more violent than if it were just ice. Rock does not melt as easily, and while the Sun's heat is overwhelming, the moment of impact could drive shockwaves deep into the solar plasma. That kind of event could amplify the risk of triggering unusual solar activity, the kind that could spill over into the rest of the solar system. A third theory takes us even further. And Some scientists suggested that 3I Atlas might be a fragment torn loose from a planet long ago destroyed in another star system. When solar systems form, they are chaotic. Young stars are violent. Planets collide, worlds shatter, and debris is thrown out into interstellar space. Over billions of years, those fragments drift through the galaxy. If 3I Atlas is such a fragment, then what we saw could be a piece of a planet that once had mountains, oceans, maybe even life. Think about that, a shard of a dead world passing silently through ours, carrying the last remnants of a place we will never know. If such an object crashed into the sun, it would not just be an astronomical event, it would be the final act of a world already lost. And then there is the fourth theory, the one that lives on the edge of mainstream science, but refuses to die, the possibility that 3I Atlas is artificial. When Oumuamua passed by in 2017, it baffled scientists with its strange acceleration and odd shape. Odd. Some researchers at Harvard openly asked whether it could have been a probe, a piece of alien technology. That debate has never been settled, and when 3I Atlas appeared, the same question resurfaced. Could it too be more than just a natural rock? Could it be a derelict probe, a fragment of an ancient spacecraft, or even a lost relic from a civilization we will never meet? Most astronomers remain skeptical, but the fact that such questions are even considered tells us how strange these interstellar objects really are. The biggest challenge is the lack of close-up data. We never had a spacecraft anywhere near 3I Atlas. Telescopes could only collect faint light as it raced past and from that we had to guess at its size, shape and makeup. In science, uncertainty invites imagination, and here imagination has run wild. Some dismiss the alien probe idea as wishful thinking. Others point to unexplained details and say we should at least keep an open mind. What makes this debate so compelling is not which theory is right, but what each possibility would mean in the event of a solar collision. If 3I Atlas was a simple comet, the sun would shred it apart in seconds, creating a brief but spectacular eruption. If it was a dense asteroid, the impact could punch harder, stirring the solar surface, and perhaps unleashing flares powerful enough to threaten Earth. If it was the fragment of a destroyed planet, then a lost world would end its journey in our star, leaving nothing but plasma behind. And if against all odds it was a piece of alien technology, then its destruction in the sun would erase any chance we had to study at a cosmic secret lost forever. Each scenario paints a different picture, but they all share one conclusion. No matter what 3I Atlas truly was, a collision with the sun would be more than a curiosity. It would be an event worth fearing, not because it would destroy the star, but because of how its energy could ripple outward into the lives of every planet and every person connected to that star. That is why astronomers do not dismiss the question. They know how fragile our knowledge is when it comes to interstellar wanderers. Every one of them has been a surprise. Everyone has challenged our assumptions, and 3I Atlas, with its uncertain nature, stands as a reminder that the next visitor may not just pass by quietly. In the end, we may never know what 3I Atlas really was. But the possibilities comet, asteroid, planetary fragment, or even probe are enough to justify asking the question, at the heart of this video, what if such an object collided with the sun? Why should we even think about the possibility of 3I Atlas colliding with the sun? The reason is simple. Interstellar objects are unpredictable. Unlike comets and asteroids that belong to our solar system bound by the sun's gravity, and moving along orbits we can trace for centuries, interstellar visitors follow no such rules. They arrive on paths we've never seen before, cut through our planetary neighborhood at incredible speeds, and then vanish back into the void. That unpredictability is the first reason to be concerned. With 3I Atlas, astronomers only had a few months to observe it before it faded from view. A short observation window means limited data, and limited data means large uncertainties. In astronomy, even a small uncertainty grows over time. A tiny error in measuring its position today could lead to a massive difference in predicting where it will be years from now. Gravity adds another layer of complexity. As 3I Atlas passed through the solar system, it wasn't moving in a straight untouched line. It brushed past the gravitational fields of planets large and small. Jupiter, with its enormous pull, could have bent its path slightly. Even Earth's weaker gravity might have nudged it off course. These deflections are often tiny, but when an object is moving at interstellar speed, a fraction of a degree today could mean millions of kilometers of difference in the future. History reminds us not to underestimate those small differences. Many asteroids have been tracked and predicted to pass Earth at a safe distance, only for later measurements to reveal a closer approach than expected. Most of those cases ended without incident, but they serve as a warning our models are only as good as the data we put into them, and with interstellar objects the data is always scarce. That is why scientists cannot completely rule out the possibility of an impact with the Sun. The probability may be low, but low is not the same as zero. And when the object in question is moving at extraordinary speed, carrying unknown material, and interacting with the gravitational pulls of multiple planets, the uncertainty is real enough to merit serious discussion. It's important to be clear this is not doomsday speculation. It is not the kind of fear-mongering headline you might find in tabloids. This is a scientific problem. When astronomers consider a collision scenario, they are not predicting it will happen tomorrow. They are running through the possibilities, asking what if, because understanding the range of outcomes prepares us for the unexpected. And the real concern isn't that the Sun would be destroyed. A star that has burned for billions of years isn't going to be ended by a rock, no matter how fast it's moving. The Sun will remain. The real fear is what happens to everything around it. A collision could trigger flares or storms that sweep across the solar system, and when those storms reach Earth, they could disrupt the delicate web of technology we depend on. Think of it like a stray bullet fired inside a crowded room. The bullet itself may not be large, but the damage it causes depends entirely on where it lands. One unlucky strike can change everything. Interstellar objects are like that. Most pass harmlessly, but the margin for error is too small for comfort. Even a relatively small impact on the Sun could act as a spark, disturbing its surface and sending energy outward. And just like a ripple spreading across a pond, that disturbance would not stop at the Sun. It would travel through space across millions of kilometers until it reached us. That's why astronomers pay attention and why we should too. So the question is not whether the Sun could survive such a collision. Of course it could. The question is how well we would survive the aftershocks. That's the reason to worry. Because in a universe where interstellar rocks arrive without warning, the line between harmless curiosity and global catastrophe is thinner than we would like to admit. When 3 Atlas was first tracked, NASA moved quickly to reassure the public it would not collide with Earth. That much was clear from the earliest calculations. The object's trajectory was steep, cutting through the solar system at an angle that would carry it away after its brief visit. There was no danger of a direct impact with our planet. But that statement came with an important caveat. The orbit of 3I Atlas was calculated from only a limited set of observations, and when data is scarce, uncertainty grows. Astronomers could predict its general path, but not with the same precision they use for familiar asteroids. The further into the future they projected, the wider the margin of error became. That uncertainty left room for debate. Within the European Space Agency, some scientists pointed out that while a collision with Earth was ruled out, a collision with the Sun could not be excluded with absolute certainty. The probability was extremely low, but not zero. When an object travels at interstellar speed, even a small deviation caused by a gravitational nudge can redirect its course in surprising ways. Harvard astrophysicists weighed in as well. Their analysis stressed how little time we had to study the object before it slipped away. Most of the data came from faint telescope images gathered over a few months. That is not much when you're trying to model the movement of a rock that has been drifting through the galaxy for millions of years. With such a thin record, even the best orbital models had to leave room for the unknown. This is why the idea of a Sun impact remained on the table, not as a prediction, but as a possibility worth testing in simulations. Science works by asking what if, and when the subject is a star that sustains all life on Earth, ignoring even remote scenarios would be reckless. NASA's official channels, including its educational YouTube content, stress the same point. More observation is always needed. Every interstellar object we have found so far has surprised us. Oumuamua accelerated in ways we couldn't fully explain. Borisov looked like a familiar comet but carried unusual amounts of dust. 3 Atlas was larger and harder to track. The lesson is clear: we cannot assume that the next visitor will behave as expected. The consensus among experts was cautious. The chances of 3I Atlas hitting the Sun were vanishingly small. But vanishingly small is not the same as impossible, and the consequences of even a small chance were large enough to justify discussion. For scientists, this was not about fueling panic. It was about respecting the limits of our knowledge and preparing for outcomes we cannot fully predict. The deeper lesson goes beyond 3I Atlas itself. The universe is wider and more unpredictable than our models suggest. For centuries, humans imagined the solar system as a closed system, a clockwork machine where everything followed neat, predictable paths. Interstellar objects have shattered that picture. They prove that our neighborhood is open to the galaxy, constantly crossed by fragments from other worlds. Each one carries uncertainty, and with uncertainty comes risk. That is why this scenario remains compelling. Not because scientists expect it to happen, but because it forces us to confront the reality of our place in the cosmos. We are not shielded. We are not separate. We are part of a dynamic galaxy full of debris and chance encounters, and every so often one of those encounters comes close enough to make us wonder what if. Which brings us back to the question at the heart of this video. If the unthinkable happened, if 3I Atlas or another interstellar wanderer did plunge into the Sun, what would actually unfold? To understand what would actually happen if 3I Atlas collided with the Sun, we need to picture the final moments of its journey. As the object drew closer to the Sun, the immense pull of gravity would begin to accelerate it, far beyond the already extraordinary speeds it carried as an interstellar traveller. By the time it reached the inner solar system, it would be moving faster than anything we can launch from Earth. Near the Sun, its velocity would soar to incredible levels, adding to the already huge amount of energy it carried. But speed is only the beginning. Once the object approached the Sun's outer layers known as the photosphere and the chromosphere, the environment would become violently hostile. The temperature at the surface of the Sun is thousands of degrees hot enough to vaporize rock and metal instantly. In the thin outer atmosphere above the surface known as the corona, the heat rises to millions of degrees. No solid material could last in such conditions. Long before it even touched the visible surface, 3I Atlas would begin to break apart and evaporate. This process, however, is not a quiet one. As it disintegrated, the object would release a vast burst of energy. Think of it like a giant ice cube tossed into a roaring fire. It does not simply vanish. It boils, pops, and sends steam in all directions. On a cosmic scale, the disintegration of an interstellar object several kilometers wide would inject a massive surge of gas dust and kinetic energy directly into the solar plasma. And that is where the real drama begins. The Sun is not a solid ball of fire. It is a churning ocean of plasma, electrically charged gas in constant motion. When something large and fast plunges into this turbulent environment, it creates shock waves. Those shock waves ripple through the plasma, stirring currents, twisting magnetic fields, and potentially destabilizing regions that were already on the edge of eruption. Solar physicists have long known that comets crashing into the Sun can trigger localized flares. We have observed it with much smaller objects. Small comets, sometimes just a few dozen meters wide, have been caught on solar observatories as they plunge into the star. The impact sends out a brief flash, a sign that even these tiny intruders can disturb the surface. Now imagine scaling that up to something hundreds or thousands of times larger. This is where the idea of a man-made or artificial solar flare comes into play. The Sun naturally produces solar flares when magnetic fields in its outer layers snap and release energy. But a violent external disturbance such as the injection of energy from a large interstellar impact could act as a trigger. It would be like shaking a bottle of soda that was already under pressure. The release could be sudden, violent, and far greater than anything caused by a small comet. If such a flare were unleashed, the results could reach far beyond the Sun itself. Solar flares often come with coronal mass ejections, massive clouds of plasma that the Sun hurls into space. These clouds carry charged particles that can travel across millions of kilometers and slam into planets, overwhelming their magnetic fields and disrupting technology. For Earth, such an event could mean widespread blackouts, satellite damage, and communication failures. To be clear, the Sun itself would not be destroyed. Stars of this size are not threatened by single collisions. The object, no matter how massive by human standards, would be insignificant compared to the Sun's bulk. But insignificance to the Sun does not mean insignificance to us. The violent interaction between 3I Atlas and the Sun's plasma could create ripples that spread across the solar system. It is also important to note that the precise outcome depends heavily on the composition of the object. If 3I Atlas was made mostly of ice, it would vaporize more quickly, spreading out into a diffuse cloud before impact. If it was solid rock or even metallic, it could penetrate deeper into the Sun's atmosphere before breaking apart, delivering its energy more suddenly and violently. Either way, the Sun would absorb the object, but the disturbance it created could vary from a minor flash to a global-scale flare. The scale of this scenario makes it unlike anything we have directly observed. The comets we have seen crashing into the Sun were tiny in comparison, barely enough to create a noticeable flare. 3I Atlas was far larger and more energetic because of its interstellar speed. That difference in size and energy is the reason scientists speculate that such a collision could cause something extraordinary, something we might call a flare on demand, even though it would not truly be controlled. In short, the physics of the event can be described in a sequence. Gravity accelerates the object to enormous speeds. The Sun's atmosphere begins to strip it apart, releasing energy. That energy drives shock waves into the plasma. The shock waves twist magnetic fields, which may then snap and trigger a solar flare. The flare could be accompanied by a mass ejection sending charged particles into space. And if one of those ejections is aimed at Earth, the effects would be felt here in the form of geomagnetic storms. This chain of events is what makes the scenario worth considering. Even though the Sun would emerge unchanged, life in the solar system might not. A star that has burned steadily for billions of years does not need to explode to remind us of its power. Sometimes all it takes is a nudge from an unexpected visitor to unleash storms that travel millions of kilometers and alter the course of our own civilization. And so, while the Sun itself would not notice the loss of 3I Atlas, the rest of us certainly would. The real danger is not the object's destruction in the solar fire, but the flare it could spark, a flare strong enough to ripple across space and touch our fragile technological world. If 3 Atlas were to collide with the Sun, the star itself would barely notice. A body just a few kilometers wide is nothing against a sphere over 1 million kilometers across, burning with the energy of billions of nuclear bombs every second. The Sun would continue to shine. But what we care about is not the survival of the star, it is the chain reaction such a collision could unleash, and how those ripples might change life on Earth. The most immediate consequence would be the flare. As 3 Atlas disintegrated in the Sun's atmosphere, its energy would twist the solar plasma and magnetic fields into chaos. That chaos could erupt as a solar flare larger than any in recorded history. We have seen solar flares before, some large enough to disrupt satellites and cause blackouts. But a flare triggered by an interstellar impact could dwarf them, releasing a torrent of radiation and charged particles that would blast through the solar system. When such a flare reaches Earth, it does not set the sky on fire. Instead, it collides with our magnetic shield. That shield usually protects us, bending most solar particles harmlessly around the planet. But if the storm is too strong, the shield falters. Energy seeps into the atmosphere, creating geomagnetic storms that ripple through power grids, communication networks, and satellites in orbit. The last time humanity experienced a storm of this magnitude was in 1859, an event remembered as the Carrington Event. Telegraph lines sparked and caught fire, operators were shocked by their equipment, and the northern lights shone as far south as the Caribbean. But the world of 1859 was simple. There were no satellites, no airplanes guided by GPS, no global internet. If the same event struck today, the outcome would be far more catastrophic. Imagine its satellites suddenly going dark, cutting off weather forecasts, global communications, and even parts of the military. GPS signals vanishing, leaving ships, planes and cars without navigation. Power grids overwhelmed by surges, transformers exploding and entire regions plunged into blackouts that could last not hours but weeks. The internet collapsing, financial systems freezing, and emergency services scrambling to operate without the digital backbone they depend on. This is not speculation for its own sake. Scientists have modelled what would happen if another Carrington-level storm hit Earth today, and the conclusion is sobering: global technology is fragile. Now imagine a flare not just like Carrington, but stronger, fueled by the impact of an object larger and faster than any comet we have seen fall into the Sun. That is the kind of event that could follow if 3I Atlas ever plunged into our star. The destruction would not be limited to Earth. Mars, with its thin atmosphere and weak magnetic field, would be even more vulnerable. A solar storm of this magnitude could strip away part of its remaining atmosphere, erasing traces of habitability and damaging any robotic missions or human settlements attempting to survive there. Other planets too would feel the disturbance, though, with less dramatic consequences than those suffered by the two worlds closest to human life. What makes this scenario particularly frightening is our dependence on technology. In the 19th century, a solar storm was an inconvenience, though a spectacular one. Today it would be a global crisis. Our lives are entangled with digital systems, satellites, and constant electricity. Hospitals rely on electronic equipment, planes rely on GPS, governments rely on instant communication. All of that could be lost in a matter of hours, and the damage would not be quickly repaired. Power grids rely on massive transformers that take months or even years to replace. Satellites cannot simply be rebooted if their circuits are fried by solar particles. Even if governments move quickly, recovery from a storm of this magnitude could take years. During that time, the global economy would collapse, and billions of people would be left without the systems they take for granted every day. It is important to stress again the Sun would survive unchanged in its eternal blaze. To the star, 3I Atlas would be a drop of rain in an ocean of fire. But for us orbiting at just the right distance to depend on the Sun's warmth, the storm it could unleash would be devastating. The star would shine as if nothing happened while our civilization struggled in the dark. This is why scientists treat the scenario seriously even while acknowledging how unlikely it is. The probability may be small, but the consequences are enormous, and in risk consequences matter as much as likelihood. We do not prepare for such scenarios because they are certain. We prepare because even a single occurrence could define the fate of our species. When we look at the potential aftermath of such a collision, the message is clear. Humanity has never lived through a solar storm of this scale. We have never seen what happens when a massive interstellar object injects its energy into the Sun. But we know enough to recognize the danger. The Sun would live on, but our way of life might not. And that is the reason this idea deserves attention. Because the real story of a Sun impact is not the survival of the star, but the survival of us. When the Sun changes, the entire solar system feels it. A collision between 3I Atlas and the Sun would not be a local event. The star is at the center of everything, its light and magnetic influence binding the planets together. If an impact triggered a massive solar flare or coronal mass ejection, the shock would radiate outward, touching every world in orbit. For Earth, the consequences would be immediate and brutal. The satellites we rely on for weather navigation and communication would be exposed to an onslaught of charged particles. Many would fail instantly, their delicate electronics fried by radiation. Those that survived might still be pushed off course, spinning out of control as their systems shut down. Without satellites, the internet, phone networks, and global communications would collapse. The blackout would not stop in space. On the ground, power grids would be overloaded by geomagnetic surges. Transformers would blow out, plunging entire countries into darkness. Trains would halt. Traffic systems would freeze. Planes would lose guidance. The modern world would grind to a halt. Mars, though further away, would fare even worse in its own way. The planet's atmosphere is thin, its magnetic field weak. Where Earth has some protection, Mars is almost defenseless. A solar storm of this magnitude could strip away gases from its already fragile sky, making it even less hospitable. For rovers and landers on the Martian surface, the blast of radiation would be devastating. Sensitive instruments could be destroyed, communication links severed. If humans had established even a small base there, they would find themselves completely exposed. Their shelters would offer little protection against the relentless stream of particles. The outer planets would not escape untouched. Jupiter and Saturn, with their powerful magnetic fields, might absorb much of the incoming energy, producing auroras larger than the entire planets. But their moons, places like Europa Ganymede or Titan, where we hope to search for life, would feel the surge directly. Radiation levels could spike, contaminating regions scientists are desperate to study. Even further out, the icy giants Uranus and Neptune would experience subtle but measurable disruptions, their magnetospheres rattled by the sudden burst from the Sun. Beyond the planets, the fleet of spacecraft humanity has scattered across the solar system would face their own apocalypse. Probes orbiting Mars, Jupiter, and Saturn could be knocked offline. Voyagers 1 and 2, still whispering faint signals from the edge of interstellar space, might go silent forever. Billions of dollars of exploration, decades of work could vanish in a single storm unleashed by an impact we never saw coming. And the effects would not vanish overnight. A geomagnetic storm does not simply flicker out. The sun's outburst could continue for days, even weeks, sending multiple waves of plasma across space. Each wave would create fresh damage. On Earth, engineers would struggle to repair power systems, only to see them fried again. In orbit, replacement satellites would be useless until the storm passed. The dominoes would keep falling one after another long after the initial impact was over. This is the essence of a solar domino effect. It is not one catastrophic strike, but a chain of disruptions spreading outward, magnified by our dependence on fragile technology. Earth would feel it first, but Mars, the outer planets, and every spacecraft we have launched would all be part of the cascade. Even worlds with no life and no cities would carry the scars of the event in their atmospheres and magnetic fields. And that is what makes this scenario so sobering. The sun would keep burning shining as if nothing had happened, but the system it governs, the planets, the moons, the machines we have sent into the dark would all suffer together. The impact of 3i Atlas would be brief, but its consequences could echo through the solar system for months, even years. Which brings us to the next question: what happens when the initial storm is over? What long-term scars might the solar system carry after such an event? That is where we turn in the next part. The immediate chaos of a solar flare triggered by 3i Atlas would be terrifying enough. Blackouts fried satellites, disrupted communication. These are the short-term consequences. But the true weight of such an event lies in its long shadow. Once the storm fades, the solar system may not return to normal so quickly. A violent impact of this kind could create a fresh cloud of plasma around the sun. This is not just a passing wave of energy, but a change to the star's environment itself. The sun constantly emits plasma in the form of solar wind, but an injection of material from a large interstellar object could alter the balance. For months, even years, the space around the sun might be thicker with charged particles than before, reshaping the conditions through which planets and spacecraft travel. This change would have consequences for the smallest pieces of matter as well. Dust and tiny asteroids orbiting near the sun are sensitive to the solar wind. Disturb that wind and their paths shift. What begins as a microscopic nudge could over years alter the orbits of swarms of debris. Some might spiral inward to be consumed by the sun, while others could be deflected outward, creating new hazards for planets in their path. The solar system is a delicate balance, and a single disruption can cascade in ways no one can fully predict. For our spacecraft, the threat would be just as real. Probes like Voyager 1 and Voyager 2, already on the edge of interstellar space, are still connected to the sun's magnetic bubble. A major flare could ripple through that bubble, interfering with their faint signals or cutting them off completely. Closer-in missions like New Horizons or probes orbiting Mars and Jupiter would be even more vulnerable, their instruments damaged by lingering radiation. The legacy of decades of exploration could be permanently scarred by the aftershocks of one collision. Even Earth itself might feel the longer-term effects. Scientists know that solar activity can influence our climate in subtle but powerful ways. Shifts in the solar wind can change how much cosmic radiation reaches Earth, which in turn affects cloud formation. If the sun were disturbed enough, we might see short-term fluctuations in weather patterns, harsher winters, hotter summers, or unpredictable storms. These wouldn't be apocalyptic changes, but they would add stress to a planet already grappling with climate instability. And the timeline is not measured in days. A single solar storm can disturb satellites for weeks. A major restructuring of the solar plasma could last for decades. Think of it as the sun sneezing. To us it's just a moment, but the sneeze sends ripples through the entire room. Dust hangs in the air, unsettling everything it touches. In this case, the sneeze of the sun would echo across the solar system for a generation. That is the unsettling truth. One collision, one moment in cosmic time could leave scars that last for years or even centuries. Humanity might recover its satellites, rebuild its power grids and restore communication, but the solar system itself would carry the memory. Altered dust belts, weakened atmospheres, lost spacecraft, and subtle shifts in climate would all be part of the legacy of 3I Atlas. This is why astronomers speak of such impacts with respect. Not because they expect one tomorrow, but because they understand how interconnected everything is. The sun is not just a star in the sky. It is the heartbeat of the system. Disturb it, and the pulse changes. And when the pulse changes, every planet, every moon, every machine we have sent into space feels the effect. In the end, the sun would go on shining steady and ancient. But around it, the balance of the system would be changed, as if one great cough had rattled every corner of the solar system. That is what makes the thought of 3I Atlas so haunting, not just the immediate storm, but the idea that one brief encounter could reshape the environment of our star for decades to come. Up to this point, we have imagined 3I Atlas colliding with the sun. But what if its path shifted ever so slightly? What if instead of being pulled into the solar furnace, it aimed directly at Mars? At first glance, that might seem less dramatic. Mars is small, cold, and distant, a barren desert compared to the living Earth. But for humanity, the impact of such a collision would be more than geological. It would strike at one of our most powerful dreams, the idea that Mars could one day become our second home. Picture it. After drifting for millions of years through interstellar space 3I Atlas curves, just enough to cross paths with the red planet. In an instant, Mars would become the stage for one of the most violent events in the history of the solar system. The collision would blast a plume of debris so vast that the sky itself would darken. Dust rich in iron oxide would rise and spread until the entire planet was shrouded in a choking red haze. From orbit, Mars would vanish beneath its own pulverized crust. The consequences would not stop with the dust. At the poles of Mars lie great reservoirs of frozen carbon dioxide and water ice. The heat of a massive impact would melt these reserves almost instantly. Rivers of meltwater could carve brief channels through the soil, filling low basins with temporary lakes. For a moment, Mars might look alive again with running water glittering under a blood-red sky. But the illusion would not last. Within weeks or months, the thin Martian atmosphere would allow the water to evaporate or refreeze, leaving behind nothing but scars. Beneath the surface, the story could be even more violent. Mars is not geologically dead. Its crust still hides magma chambers, and its largest volcano, Olympus Mons, towers as the tallest mountain in the solar system. A sudden injection of heat and pressure from a colossal impact could awaken ancient volcanic systems. Lava flows might surge across the planet, adding fire to the storm of dust and ice. Instead of a second Earth, Mars would resemble a wasteland caught between ice and fire. The scale of destruction would be far beyond anything we know from Earth. The impact that killed the dinosaurs 66 million years ago carved a crater over 150 kilometers wide. On Mars, with its lower gravity and thinner atmosphere, 3I Atlas could gouge a basin even larger, a wound visible from space for eternity. The shock waves would circle the entire planet, shaking its crust and cracking its surface. Any fragile atmosphere Mars retained would be stirred, thinned, and blown away into space. For scientists and explorers, the tragedy would not just be geological, it would be human. For decades, Mars has stood as our most promising outpost beyond Earth. Space agencies and private companies alike have dreamed of building colonies there, using its soil, its ice, and its proximity to the sun as resources for survival. If 3I Atlas slammed into the planet, those dreams would evaporate in a moment. The fragile hope of terraforming already a challenge measured in centuries would be set back indefinitely. Instead of becoming a world where human beings could build cities under domes, grow food, and slowly reshape the climate, Mars would be transformed into a graveyard. Its surface would be poisoned by radiation and choked by dust. Its water would vanish as quickly as it appeared, and its crust would remain unstable for generations, prone to quakes and eruptions triggered by the lingering heat of the impact. This is the cruelest twist of the scenario. While a collision with the Sun might leave humanity scrambling to repair its technology, a collision with Mars would rob us of our future. It would destroy the one place we have looked to as a backup world. It would tell us in no uncertain terms that the universe does not care about our plans. Mars would not be our refuge. It would be our tombstone. The psychological blow alone would be enormous. For more than a century, Mars has occupied our imagination. From H.G. Wells to NASA, it has been the symbol of life beyond Earth, whether alien or human. Seeing it obliterated by an interstellar rock would remind us how fragile even our best hopes are. The planet we thought could save us could just as easily betray us, turning into a monument to human ambition cut short. And yet in that destruction, there would be lessons. Scientists would learn more about planetary geology than ever before. Instruments watching from orbit could study the unfolding chaos in real-time, recording data about impact's atmosphere and crust that we could never replicate in laboratories. But these lessons would come at a terrible cost. Knowledge, yes, but the loss of Mars as a potential home. So while Earth would survive, untouched humanity would lose something irreplaceable. The dream of a second world, a frontier to carry us beyond our fragile planet, would be erased in an instant, and with it our illusion of safety. If Mars is not beyond the reach of cosmic catastrophe, then neither are we. This is why the scenario of a Martian impact resonates so deeply. It's not about the destruction of a barren world. It's about the collapse of our vision for the future. Mars, the red planet we hope to tame, could instead become the ultimate reminder that in the cosmos, safe havens do not exist. Let's imagine a different future. A century from now, humanity has finally achieved what generations of dreamers once thought impossible. SpaceX, NASA, and other agencies have joined forces to build the first colonies on Mars. Under vast domes, settlers grow crops in carefully controlled greenhouses. Solar farms stretch across the dusty plains, collecting energy from the weak but steady sunlight. Water is harvested from polar ice and recycled endlessly to sustain the fragile human outposts. For the first time, Mars has become more than a distant red dot in the sky. It has become home, and then without warning, everything changes. The interstellar traveller 3I Atlas, nudged onto a slightly altered course, does not pass harmlessly by. It strikes Mars with unimaginable force. In a single moment, the vision of a second world collapses into chaos. The first to go are the greenhouses. Transparent domes designed to let in sunlight are shattered by shock waves. Crops, once the lifeline of the colony, are reduced to ash and dust. The settlers rush to seal airlocks, but the planet outside is already changing. Dust clouds rise into the thin Martian sky, blotting out the sun. Within hours, the world is plunged into a permanent twilight. Power begins to fail next. Solar panels, once efficient enough to run entire colonies, are coated in a thick blanket of iron-red dust. No light reaches their cells. Batteries drain. Generators sputter. The infrastructure of survival, dependent on steady power, starts shutting down one system at a time. Oxygen recyclers slow. Heating units falter. The carefully maintained balance of life support begins to unravel. Oxygen itself becomes the next crisis. With no plants left to refresh supplies and power reserves dwindling, every breath is borrowed time. Tanks that once offered security now tick down towards zero. In underground habitats, colonists begin rationing air-cutting movement to conserve what little remains. The thin Martian atmosphere offers no help. It is nearly all carbon dioxide, useless to human lungs. Slowly, inexorably, the colony suffocates. Food too runs out. With greenhouses destroyed, there are no crops, no harvests. The small stores of emergency rations cannot last long. In desperation, settlers attempt to stretch supplies, but hunger soon gnaws at the community. Children grow weak. Adults work themselves to exhaustion, knowing that no supply ship from Earth can come to the rescue. The distance is too great. Communication delays alone stretch to minutes, but even if Earth hears the call help, would take months to arrive, months the colonists do not have. Radiation becomes another invisible killer. Mars, already lacking a strong magnetic shield, is bathed in cosmic rays, amplified by the solar storm unleashed by the impact. Protective shelters hold for a while, but as power fails, shielding systems break down. The colonists are exposed to doses that weaken their bodies, sicken them, and accelerate their decline. Psychological collapse follows close behind. At first, there is unity, a determination to survive, to adapt, to hold out until help arrives. But as days stretch into weeks, as the oxygen runs thinner, and the food stores empty, hope fades. Arguments break out. Morale shatters. The dream of Mars as humanity's sanctuary transforms into a nightmare of isolation. Some imagine desperate escapes. They talk of launching return ships, but the dust storms and radiation make such attempts impossible. Others cling to the fantasy of deep underground shelters, but no one has the time or resources to build them. In truth, there is no escape. Mars, once seen as humanity's next home, has become a prison. The end comes not with explosions or dramatic battles for survival, but with silence. One by one, the lights of the colony go dark. One by one, the voices calling Earth for help fade into static. The settlers, the pioneers of a new frontier, die not in glory but in suffocation, starvation and despair. And on Earth, the loss is felt as both tragedy and warning. Humanity's first great colony, the outpost that was supposed to guarantee our survival beyond Earth, is gone. Not destroyed by war, not undone by human error, but wiped out by the indifferent strike of a rock from another star. The lesson could not be clearer. In the cosmos, distance does not mean safety. Dreams of escape are fragile. Even our boldest steps beyond Earth can be undone in a moment by forces we cannot control. Mars, once the symbol of hope, becomes the grave of our ambition. This is why the idea of a Martian impact is more terrifying than a solar one. The Sun would survive. Earth might even recover. But if Mars were destroyed while we lived there, humanity would be confronted with the ultimate irony. Our second chance at survival, our backup plan for the future, would turn into a mass grave. The very planet we trusted to save us would become our tomb. And so when we think about 3I Atlas colliding with Mars, the fear is not only scientific, it is deeply human. It reminds us that no matter how far we travel, no matter how advanced our technology becomes, we remain vulnerable. The universe is not a sanctuary. It is a wilderness, vast and unpredictable. And in that wilderness, even the boldest of dreams can end in silence. After imagining all these catastrophic possibilities, it is time to step back and listen to what the scientists themselves say. From the beginning, NASA has been clear the orbit of 3I Atlas does not point toward the Sun. The data we have, though, limited, shows that the object was always on a trajectory that would take it past the star, not into it. By every official calculation, the probability of a collision is not just low, it is vanishingly small. So why do astronomers still study this scenario? Why spend time and effort thinking about something that almost certainly will never happen? The answer lies in the way science approaches risk. In science, low probability does not mean no probability. Even if the odds are 1 in a billion, if the consequences are enormous, then the scenario deserves careful thought. This is why agencies like NASA and ESA continue to run models, publish papers and track interstellar objects with such urgency. The point is not to predict doom, but to prepare for surprises. Every time a new visitor enters our solar system, it challenges our understanding of celestial mechanics. And every time we model its path, we sharpen the tools that might one day save us from a real threat. Many scientists echo this view. They acknowledge that 3I Atlas itself is not a danger, but they emphasize the importance of treating it as a case study. Interstellar objects do not follow familiar orbits. They move faster, their trajectories are harder to predict, and the data windows are short. By analyzing 3I Atlas, astronomers learn how to refine their methods, how to account for uncertainties, and how to handle the unexpected. Some researchers describe it in simple terms: you don't buy fire insurance because you expect your house to burn down tomorrow. You buy it because if the fire ever comes, the loss would be devastating. The same logic applies here. We do not model a sun collision because we think it is likely. We model it because if it ever happened, whether with 3I Atlas or another object in the distant future, the outcome could change civilization. There is also the humbling reminder that our knowledge is never complete. When Oumuamua was first discovered, scientists struggled to explain its unusual acceleration. When Borisov arrived, it looked like a comet, but carried properties we had never seen before. 3 Atlas. Larger and faster added its own puzzles. Each one has reminded us that the universe is not bound by our expectations. What we call unlikely often turns out to be only unobserved, and that is why, even as NASA reassures the public that there is no imminent danger, researchers keep their eyes open. They know that complacency is dangerous. They know that certainty is an illusion. In a cosmos as vast and chaotic as ours, it only takes one anomaly to overturn the models. The consensus then is clear but nuanced. Yes, the chance of 3I Atlas colliding with the Sun is effectively zero. No, we should not lose sleep over it. But yes, it is still worth thinking about, because in the balance of risk, small probabilities and massive consequences deserve attention. That is the essence of the scientific view, not alarmism but caution. Not fear but preparation. A recognition that the universe is larger than our certainty, and that humility in the face of the unknown is the wisest course. So while the official verdict is that 3I Atlas is no threat, the conversation it sparks remains valuable. It forces us to think about what we would do if the impossible happened. And it reminds us that even when the numbers are close to zero, the story is never finished. Not every scientist views a potential impact as pure disaster. Beyond the mainstream view lies a set of fringe theories, ideas not widely accepted, but fascinating enough to force us to think differently. Among them is one of the oldest and boldest concepts in astrobiology, panspermia. The panspermia hypothesis suggests that life might not begin in isolation. Instead, it spreads. Rocks carrying microbes, fragments of planets or frozen comets could act as seeds carrying the ingredients of life from one world to another. If 3I Atlas carried organic molecules, the building blocks of biology, then a collision with the Sun might scatter them across the solar system. Plasma eruptions could launch particles outward, some eventually drifting toward Earth-Mars or the icy moons of Jupiter and Saturn. In this way, a destructive impact could paradoxically act as a gardener, planting the seeds of life in unexpected places. A few researchers have speculated along these lines. They point out that organic molecules have already been found on comets and asteroids within our own system. If those molecules exist here, why not in objects formed around distant stars? If 3I Atlas was rich in such material, its fiery end might be less of a death and more of a rebirth, a way of sharing its chemistry with every corner of our planetary family. There is also a philosophical angle. Human beings often think of destruction as final, but in the cosmos, destruction and creation are two sides of the same coin. Stars explode in supernovae, scattering the heavy elements that form planets and people. Collisions shatter worlds, but they also create new moons, stir atmospheres, and drive evolution. In that sense, the annihilation of 3I Atlas in the Sun might not be the end of its story, but the beginning of another. The seeds it carried, whether biological or chemical, could outlive the rock itself. Of course, not all fringe theories are about life. Some wander into far stranger territory. When Oumuamua was discovered in 2017, a handful of scientists from Harvard suggested it could be a piece of alien technology, a probe, or a fragment of a spacecraft. That idea was controversial, criticized, even ridiculed. But it made headlines for one reason: there was no clear explanation for Oumuamua's odd acceleration. If that question remains open, then it lingers over 3I Atlas as well. Could it too have been artificial? Could we have been watching not just a rock but a relic? If so, a collision with the sun would be more than a physical event. It could be a test or even a message. Some speculate that if advanced civilizations exist, they might send probes across the galaxy not to communicate but to observe, to experiment, to trigger reactions. What if 3I Atlas was one of those? What if its end in the sun was not an accident but part of some vast, incomprehensible plan? Most astronomers dismiss this as unlikely, and yet the fact that such questions are even asked shows how mysterious interstellar objects truly are. When data is scarce, imagination fills the gaps, and imagination can be as unsettling as science. In the end, whether 3I Atlas was a comet carrying the seeds of life, a fragment of a long-dead planet, or a piece of alien engineering, the result is the same. A collision with the sun would remind us of our ignorance. We do not fully understand what drifts through the galaxy, what secrets those objects carry, or what roles they might play in the grand story of life and death. And perhaps that is the real lesson of these fringe theories. They push us to admit how little we know. They remind us that in the vast theatre of the cosmos we may not yet understand the script. Destruction might hide creation, endings might be beginnings, and the universe may hold designs far beyond the reach of our imagination. Now imagine the opposite. 3I Atlas does not strike the sun. It does not crash into Mars. It does not collide with Earth. Instead, it simply passes by, silent, harmless, forgotten. At first glance, this seems like the best outcome. No destruction, no solar flares, no catastrophe. The world breathes a sigh of relief and the headlines move on. But is that really comforting, or is it in some ways far more disturbing? Because what lingers after 3 Atlas is gone is not relief. It is unease. The unsettling truth is that objects like it are not rare. We have already seen 3 in just a few years: Oumuamua in 2017, Borisov in 2018, and then 3I Atlas in 2019. If we can detect 3 in such a short span of time, how many more have slipped past us unseen? How many wanderers cross our skies without ever being noticed? Astronomers admit this openly. We only see what our telescopes happen to catch. Most of the sky is unmonitored at any given moment. Most of these objects are faint, dark, and fast. It is likely that for every interstellar visitor we find dozens more go undetected, and if even one of those happens to cross paths with a planet or the sun, we might never see it coming until it is too late. That is the haunting part. Silence does not mean safety. Silence means ignorance. When 3I Atlas fades back into the darkness of space, it leaves behind the reminder that the galaxy is full of wanderers just like it, and we are blind to most of them. This realization gnaws at the imagination. We like to think of the solar system as a predictable clockwork, a place where planets and moons move in elegant orbits, and nothing unexpected ever intrudes. But the truth is different. The solar system is open, it is porous. The walls we imagine around it are not walls at all. Beyond Neptune, beyond Pluto's space is not empty. It is connected to the rest of the galaxy, and that galaxy is restless. The thought of this hidden traffic raises a deeper fear. What if the next visitor is larger? What if it is on a path we do not detect until the final moment? What if 3I Atlas was not a warning but merely one of millions? The silence becomes oppressive because it hides the sheer scale of our vulnerability. In some ways, a collision would almost be easier to process. At least then we would see the event. We would study it. We would know what it means. But when nothing happens, when the object simply drifts past and vanishes into the void, we are left with nothing but questions. Where did it come from? What else is out there? How many more are on the way? And why do we see so few when logic tells us there must be so many? It is this gap between what we know and what we suspect that frightens scientists most. We know 3. We suspect millions. That gulf is the true danger. Not the fire of a solar flare, not the dust storms of Mars, but the endless unknown of a galaxy we barely understand. Think of it like hearing footsteps in the dark. If the footsteps rush toward you, the threat is clear. You react. You defend yourself. But if the footsteps pass by, if they fade into silence without explanation, the fear lingers longer. What if they return? What if they were never alone? That is the fear of Three-Eye Atlas slipping past untouched. And so, in this scenario, the real story is not the absence of catastrophe. It is the presence of uncertainty. An interstellar traveller came past through our neighbourhood and left us no clearer about our safety than before. The silence it leaves behind is more unnerving than an impact because it suggests a pattern, a galaxy teeming with wanderers we cannot track, cannot predict, and cannot stop. Scientists call this a background risk. It is not a single threat, but a constant one, an ambient unease, the kind of risk that never makes headlines but keeps researchers awake at night. Because one day silence will break. One day one of these wanderers will not just pass by, and the truth is we may not be ready when it happens. This is why the story of Three-Eye Atlas remains so haunting, even if it never collides with anything. Its quiet departure does not close the book. It opens it. It reminds us that the galaxy is not a place of order, but of chance, and chance does not always favour us. So perhaps the most terrifying scenario is not the impact itself. Perhaps the most terrifying scenario is this: Three-Eye Atlas fades into the dark and we realise that it was only one of countless others. The silence of space is not peace. It is a reminder of how little we know and how fragile we are beneath the endless night. In the end, nothing happened. Three Atlas slipped past untouched, disappearing back into the deep night between stars. No solar flare tore across the solar system. No Martian dust storm buried colonies that do not yet exist. No collapse of Earth's technology left us in darkness. The world continued unaware. To most people it was as if the object never existed at all. But for those who watched, those who studied, those who wondered, the lesson was unforgettable. The Sun, Mars, Earth, all of them fragile in their own way. A star so vast it dwarfs our imagination could still be shaken. A planet that has stood for billions of years could be scarred in an instant. And our own Earth, teeming with life and technology, could be undone not by war or plague, but by a chance encounter with a wanderer from another star. The collision never came, but the thought of it taught us something more important than the event itself. It reminded us that certainty is an illusion. We like to believe we can predict the heavens, that the sky is charted, that the cosmos follows rules we already understand. But every interstellar visitor tells us otherwise. They appear without warning, stay for a moment and vanish again. They remind us that we live not in a sealed system, but in an open cosmos, and the open cosmos has surprises waiting. Science at its heart thrives on these surprises. The purpose of studying Three-Eye Atlas was never to predict doom. It was to learn to sharpen our tools to prepare for what might come. The scenarios we imagined, collision with the Sun, devastation of Mars, blackouts on Earth, were not prophecies. They were thought experiments, ways of asking how fragile our civilization really is and how ready we are to face the unknown. And what we learned is sobering. Our technology is powerful but vulnerable. Our dreams of colonizing other planets are bold but fragile. Our place in the solar system feels secure, but in truth it is only borrowed time. Yet in that recognition lies strength, for only by admitting our fragility can we begin to defend it. Only by imagining the worst can we prepare for it. This is why hypothetical scenarios matter. They do not frighten us for the sake of fear. They awaken us. They remind us that vigilance is the price of survival. They tell us that humanity cannot afford to stop watching the skies. Every telescope, every survey, every model we run, they are not luxuries. They are lifelines. Because the next Three-Eye Atlas may not pass quietly. The next visitor may not miss. and when it comes, we will want to know we have done everything possible to be ready. There is also a deeper, almost philosophical lesson. In every scenario, we explore destruction carried with it the seed of something else, a solar flare that might scatter life's building blocks, a Martian impact that might teach us about planets, a silent passage that might remind us of the countless others still unseen. Endings and beginnings are not separate in the cosmos, they are intertwined. The death of one star fuels the birth of another. The shattering of one planet might give rise to moons. Even the silence of an object passing by is not empty. It speaks of the vast, restless galaxy beyond. So perhaps the greatest lesson of Three-Eye Atlas is not about doom at all. It is about humility, a reminder that our species, for all its ambition, is small, a reminder that certainty is a luxury we cannot afford, and yet within that humility lies a quiet strength, because though we are small, we can imagine, we can prepare, we can hope, and in the end, hope is what sets us apart. The universe may be indifferent, but we are not. We watch, we learn, we wonder, we dream. That is our defense against the silence, our answer to the chaos of the cosmos. So as this story closes, we leave Three-Eye Atlas drifting back into the unknown, a traveller whose shadow forced us to look harder at ourselves. It did not destroy us. It did not even touch us. But it reminded us of truths we cannot ignore. The sun still burns. Mars still waits. Earth still spins beneath its fragile shield. And humanity, small, uncertain, but filled with hope, continues to gaze upward, knowing that the next visitor is already on its way. We are small, we are fragile, but we endure. And in that endurance, in that spark of hope, we find our difference. That is what makes us human. That is what keeps us alive beneath the endless sky.